Hi everyone, my name is Adedayo Sanni, a fourth-year graduate student here at Wayne State University. Welcome to the Rury Group. Here in the Rury Group, we study the structural properties of various kinds of materials, including, but not limited to, hybrid organic-inorganic perovskites, ferroelectrics, and polaritons. I will show you a little bit of what we do in the lab and how the lab operates. Walk with me as I show you the sections of the lab. In this section of the lab, we have the spectroscopic section, the ultra-fast section, where we have over here a titanium sapphire laser that puts out pulse on the duration of 1/10 of a trillionth of a second. That is a very fast pulse. This fast pulse allows us to resolve fast phenomena going on in these materials, which are very important in next generation devices. On one optical table here, we have the time domain terahertz spectrometer, which allows us to resolve low frequency vibrations in the far IR region. On the other side of the optical table, we have the pump probe spectroscopy setup, which allows us to resolve fast processes in electronic transitions. I will show you a feel of the lab using the time domain terahertz spectrometer. Our terahertz is generated by focusing 800 nanometer light on hair, and the second frequency of the 800 nanometer light drives electron away and back to hair. That huge signal you are seeing on the screen right there is the terahertz waveform of hair. We use this technique to characterize our materials, most especially the hybrid organic-inorganic perovskites that we study in this group. A quantum well structure that is essentially layers of non-interacting organic atoms spaced by organic cation. On this other side of the lab, we synthesize our materials. Most especially, I work on the hybrid organic-inorganic perovskites, which we can make into different material forms, into thin films and single crystals. We make these single crystals using a layered approach, which I will show you now. What we do is we layer two different solvents with different densities, which creates an interface where our reaction can take place, and we can control the stoichiometries of the precursors. This allows us to introduce defects into these materials. The defects we introduce into these materials give rise to broadband emission. These broadband emission are useful in next generation light emitting diodes. This synthetic approach allows us to create various kinds of self-assembled quantum wells, which are easily made from this layered approach. As you can see, the color contrast between two analogous materials shows that we are tuning the band gap of these materials using this very simple synthetic technique. We also have the capabilities of studying the temperature dependence of this broadband emission as we create them from synthetic roots. As we change the temperature, we observe that our broadband emission becomes intense, which is important in the next generation light emitting diodes. Finally, we solve the single crystal structures of our materials using the Bruker X8 diffractometer that we have here at Wayne State University. So, I hope you have enjoyed the tour of the Rury Group and had a feel of the research we do here in the Material Structural Dynamics Laboratory. Hope to see you next fall, where we will be doing awesome science together. Thank you.